Welcome back. We are now looking at our third lesson in our environmental chemistry course, Chapter 4, Energy from Combustion. And we're looking at section 4.6 where it says energy changes at the molecular level. You know, reactions involve breaking bonds and forming new bonds. I mean, that is the heart of chemistry, is breaking the bonds of the reactants, rearranging those atoms, and then forming new products. It's the breaking and forming of bonds that dictates if a reaction will be endo or exothermic, heat absorbing or heat releasing. I remember studying in our last chapter about the ozone layer and just looking at how carbon dioxide with its polar bonds, we talked about those polar bonds being able to spring, like a spring, they'd be able to stretch and come back. We'd be pulling out potential energy, turning it into kinetic energy. We can compress or stretch these bonds. The infrared type of radiation, which is of lower energy, can be absorbed in these bonds, and that's what's contributing to the greenhouse effect, is storing extra energy in the bond of the molecules of CO2. But I also remember discussing that if UV radiation, which is of higher energy, actually were to hit these bonds, they actually break. So in the presence of a high energy, we can take these chemical bonds and stretch them so far that they actually break. Breaking bonds requires energy. So remember, this is a storage tank, a potential energy storage tank. If we break the bond, input of energy is required, and now we've released the harnessed energy of that chemical bond. And if you look at your text with me, we see what's given to us on table 4.4, and this is on page 176 if you find that helpful in your text. What it does is allow us to find out how much energy it takes to actually break a bond between the following atoms. So let's suppose we have a hydrogen attached to a hydrogen. In other words, just a molecular molecule of hydrogen here, H bonded to H. How much energy does it take to break apart that single covalent bond? Well, it would take 436 kilojoules for every mole of that molecule. If we had a hydrogen attached to a carbon in a single covalent bond, and I wanted to break apart a CH bond, it would require 416 kilojoules per mole of energy. And so forth. If I had a bond between carbon, single bond carbon, and I wanted to break that bond, it would require actually a little less energy, 356 kJs per mole. So these are all single bonds between the elements, alrighty? And notice when you start to get elements where they don't connect, for instance, a sulfur and an oxygen don't form a bond, so you just see a line there. Now in terms of multiple bonds, it takes a little more energy. Notice where it said up here, if I had a C, single bond C, and it's in a molecule of ethane, right, from our earlier lesson, CH3, to break this single bond was 416, CCC is 356 kJs per mole. If I had a double bond C, it's going to take more energy to break both of those shared pairs of electrons. We see that written as 598 kJs per mole. This is triple bond C, recorded as 813. And so forth. N double bond, N triple bond, C double bond N, C triple bond N. Here's O double bond O, C double bond O, C triple bond O, which we're looking here. So single bonds and multiple bonds, each one of those are going to be used to calculate how much energy it requires to break a bond. So for instance, just kind of see why we need to know this. Earlier we had said, how much energy does it actually take for this reaction to go? Let's just take an earlier equation where we had methane, our simplest of all hydrocarbons. Write that out with me. methane is methane, right? CH4. We're going to react that with oxygen. In a combustion reaction, out comes carbon dioxide and water. This combustion pattern, very familiar to us, isn't it? We add oxygen when burning a fuel, producing the byproducts, these global warming gases here, CO2 and H2O. And I want to know, what is the heat of this reaction? In kilojoules per mole, will it be exothermic or endothermic? How much heat is going to be either absorbed or generated, released from this reaction? We obviously know that a burning reaction is going to release energy. I mean, I just know that. That's the purpose of burning fuel, is to release the energy. I'm already making a prediction that my sign here will be negative. I also know that right now what's probably bothering you is we're not balanced, right? So we need some coefficients here. One carbon, that looks great. 4 H's. I better double the waters to get 4 H's. Counting the O's, we have 2 plus 2 more. Here's our balanced chemical equation for the combustion of methane. Now, how do I go about actually calculating how much heat is going to be released from this combustion? And the secret lies in these chemical bonds. Consider with me the Lewis structure of the molecule CH4. Remember, we drew this earlier in our notes. We have carbon single bonded to H all through this molecule. Carbon single bonded to H. So if I think about what I have 4 C single bond H. Right? let me just change color. I have 1 CH bond. I have 2 CH. There's the third, and there's the fourth. I have 4 CH bonds. If I'm going to break a CH bond, how much energy did it take? A carbon, I need to go up just a little further. A carbon hooked to a hydrogen. We can get that either way, right? Carbon to hydrogen is 416 kJs. We have 4 of them to break. So 416 for each one of these. Since we have 4, we're looking at a net total of 416 times 4. So this is the first amount of energy contained in those chemical bonds of methane. Let's keep going. Here's our next reactant. It's O connected to O. Remember this molecule when we drew molecular oxygen? It was O double bond O. Molecular oxygen with 6 valence electrons, lives in group 6A, had to share 2 pairs so it would obtain the octet that it so desired. So I actually am drawing 2 molecules of O2. Each one of those is double bonded. So O double bond O, O double bond O. That's this illustrated. So how much energy is that going to take? And O double bond O is 498. 498. So here's what we have here. Let me get that caught up. So here we have 2 units of O double bond O. Here we had 4 carbon hydrogen. So let's just figure out some math quickly. Let me grab my calculator. I'm going to hit 416 times 4. And I'll record that as, let me change just to blue. We'll say 1664 is the energy contained in those 4 CH bonds. I'm going to add, let's see, what's 2 times 498 is 996. So the energy contained in the reactants is the sum of 1664 plus 996. I'm adding together all of the bonds, 2660 kilojoules of heat. And what this is just kind of drawing a line here. This is the reactant side of our equation. All of the energy being stored in the bonds over here. Alrighty, let's consider what's going on this side now. We have a carbon dioxide molecule. We've drawn this before where we've had C double bond O in either direction. This is the molecule of the Lewis dot structure of carbon dioxide. So let's just pause a moment and see what's going on here. We have C double bond O. See that right here? C double bond O is 803. I don't want the single bond value. It needs to be the double bond value. So I have 803. Let's record that before I forget. How many do we have? Well, I can see that there is a C double bond O here and a C double bond O here. So I have 2 storage tanks of C double bond O. Alrighty, how about a water molecule? I have to work down the page just based on space. So let me go back to purple. We know that a water molecule, when we drew a water molecule, we've studied from the molecular geometry that it's a bent molecule. So I know that it's H single bond O single bond H. But there's 2 of them there, isn't there? So I'm just going to draw that for us. Just the visual helps so many students as we're counting the number of bonds. And what do we see in 2 water molecules? Well, I count 1 OH single bond, 2 OH single bond, 3 and 4 OH single bond. So I have 4 groups of OH single bond. Let's use our table. What is an OH single bond? O connected to H? Well, that's 467 kilojoules of heat. 467. Let's do a little math here and see what the energy stored on the reactant side. So that's what I'm doing, is dividing all of the molecules on the reactant side and all of the molecules over here on the product side. The sum of the reactant so far, and over here I need to sum the 2 values of the product. So I'm going to take 2 times 803, and that's 1606. That's the energy coming from carbon dioxide. 4 times 467, that's 1868. And that's all of the energy stored from the 4 single OH bonds. Let's sum those together, shall we? So 1606 plus 1868, and we'll find a total. So on my calculator of 1868, so I'll go plus 1606, and I'm finding 3474. Alrighty, so now what do we do with this information? I know that the chemistry says reactants break bonds. I mean, that's what we're doing. We're breaking the bonds. We're going to rearrange them, and we form new bonds. Reactants get rearranged when they make products. So I'm just making a note here that we break the bonds of the reactants and we put them back together in a different organization as the products are made. So all in all, this is what we're going to use this information for. I can calculate the delta H, which I understand to be a word called enthalpy. In chemistry, enthalpy is a thermodynamic word to simply mean heat content of a chemical change. There is another word we introduced earlier called entropy. And entropy is also a thermodynamic quantity. We never said it, but just in case you know, entropy in chemistry gets an abbreviation of S. It has nothing to do with this particular problem, but I'm just reminding us of a word we heard earlier in the lesson that has to do with the random or chaotic nature. Things just like to become disorganized. That's the natural tendency, is to create disorderly, chaotic nature. It wants to become disorganized. So I'm just making that note, just a separate little note here about entropy, a second thermodynamic quantity. But enthalpy, the heat of reaction, has a symbol H for heat, enthalpy. What we can do to find the enthalpy of an entire reaction is take the sum of all of the heat content from the products and subtract from it all of the heat content that we found contained in the reactants. Products minus reactants. And I'm going to put this in a bracket to remind us that products minus reactants, that I have a lot of math to do inside them. It's the sum of all of the heat content of the products minus the sum of all of the heat content found in the bonds of those reactants. So remember, products were over here. I'm going to visually make that green to remind us 34, 74, 3474 was the heat content of our products minus the heat content. Let's just change color. Let's make this purple. 2660 was the heat content found for the reactants. $34.74 minus $26.60 gives me a value of 814. And that's in kilojoules. We understand that burning was an exothermic process. So as the course of this reaction occurred, 814 kilojoules of heat energy was released for every mole of methane. Exothermic, as all combustions are. Let's take a quick peek at a next example. This is an example where, this didn't print just right, 2 molecules of hydrogen and a molecule of oxygen are combining to form water. And remember, there's 2 moles of water, 2 moles of H's. So when I consider what's breaking, on the reactant side, I have 2 molecules of HH and 1 molecule of O double bond O. And remember what we're able to do. If we think about breaking bonds, you see that we're breaking bonds. To break a bond inputs energy. Notice that it's taking energy to break apart the reactants. But forming energy, putting the products back together, is releasing the energy. And notice what we're doing. We're taking the sum of the products minus reactants. And so if I look at 2 molecules of H2, and from our chart, it's just showing us how they calculated that. 2 units, each at 436. Up here we have an O double bond O. It had a value of 498. We sum the content of all of the energy contained in both H's and the O double bond O. And we're going to subtract then this value 4 times the 467 kilojoules. And when I do that, we see that it's releasing energy. And I see the net difference here. The net difference would be the sum of the sum of products minus reactants, and that difference is 498. Notice what they've done here, and this is worth highlighting, and I'm going to back the slide up as well. Notice that these are all positive signs, the positive signs because we are breaking bonds. But notice how they made this a negative because we're forming bonds. And therefore, when I took the values, the sum of the products, which would have been over here, negative 1868 minus, and then the sum here would have been 872 plus 498, and you can see where it ends up to be a net negative 498. Here, back on our previous slide, considering that, notice that on this side, because we're forming bonds here, technically this is a negative sign, and over here these would be positive signs from our chart. So if we consider this value being negative, placing that into your negative product here, you'd have negative minus a smaller value, and you can see how it's negative then overall. But our intuition also told us that because it was exothermic, as all combustions are, we know it had to come out to be a negative sign. So reactants, because we're breaking bonds, we know that it's a positive value from our chart. On the product side, because we're forming bonds, make them a negative value on your chart and take the products minus reactants to find the overall change of your compound. Here's a practice where we have ethyne, which is acetylene. So just to get an idea, I'm going to draw this for us. C triple bond C, H, H is what we call ethyne. And if you'd like to follow, this is on page 178 as an example. It's taking your turn on number 4.16 to see where I'm pulling this example from. Alrighty. So I have HC triple bond C single bond H plus O2, and I'll just write that as O2, forming carbon dioxide and water. And just borrowing from this page 178, we can see the coefficients to balance this. 2 molecules of our fuel called acetylene plus 5 molecules of our diatomic oxygen yields 4 molecules of our carbon dioxide and 2 molecules of our water. A 2 to 5 to 4 to 2 balances that overall equation. We'd like to know the delta H for this reaction. What is the enthalpy change, the overall chemical heat content as this fuel combusts? Of course, we're not expected to memorize, but we should know where to find table 4.4. And if you have that handy, that's what we're going to end up using. It's on page 176 or just a couple slides back in our PowerPoint presentation. So we need to look up the following bonds. In this molecule, there are 2 H single bond C's. See them? H single bond C, H single bond C. And since there's 2 overall, we're going to carry that through with the coefficient. I'm going to look up for us HC. HC is 416. So 416 is its content. So really I'm hitting 4 times 416. I'll do that for us. 4 times 416, that's 1664. What else do we have in that molecule? Well, I also see a C triple bond C. And I see just one of those in that molecule. C triple bond C, don't forget that coefficient there as well, but I need that C triple bond C. That value is 813. So let me record that. So because we have two molecules, we have in each one C triple bond C, each at 813, so I have to double that. 813 doubled is 1626. And so all of the energy contained in two fuel molecules would be the sum of 1664 plus 1626. And that's 3290 kilojoules. And that's our first molecule, 2 units of acetylene. How about the 5 oxygens? Well, we need to look up an O double bond O. O double bond O, that's 498 right here. So 498. So an O double bond O is 498. But I have 5 molecules of them. So 5 times 498 is 2475. Alrighty. So where are we at so far? I have a combined total on this side of 3290 plus 2475. So on this side, 5765 kJs. It's all of the energy stored in the bonds. Now we're going to break those bonds, so I know that this side is positive. It takes energies to break bonds, so positive sign. Now we're going to rearrange them. Let's see what we have going on here, and I'll just make this green. I have 4 molecules of CO2. In each molecule, I count 1, 2 C double bond O's. And a C double bond O has a value of, C double bond O is 803. So what will I need to multiply here? 4 units, but 2 of them in each unit, so that's 8. 8 times 803 is 6424. Remember now, we are forming bonds, and so I just wanted to note that these are going to be negative signs. Positive when we break them, negative when we form them. What's going on over here with the water? Well, in each water molecule, I have 1, 2 OH bonds, right? So I have the coefficient of 2, and in each molecule, I have 2 O single bond H. And what's the value of O single bond H? 467, it looks like. 467. So 2 times 2 is 4. So really what I'm hitting is 4 times 467 for a total heat content there of 1868. But I'm going to show that it's negative because we are breaking and forming bonds. So on this side, just remember that on this side, the bond energies will be positive, and on this side, the bond energies will be negative. And we'll take the sum of products minus reactants. So let's sum what we have so far. We have negative 6424 plus negative 1868 equals negative 8292, and that's in a kilojoule. Alright, so I'm going to take this heat of reaction, and now I just want to emphasize something that I've done on this example. Remember how we made all of the positive signs when we are breaking bonds from our chart on page 178, and we've already made the negative signs for the bonds forming over here on products. So if you make the products negative, because we are making new bonds, and you make the reactants positive because it takes energy to break bonds, I just want you to sum the two values. So I'm going to take the negative 8292 kJs, and because it's negative, because we were breaking or we're forming new bonds on the product side, and if we make this negative because it's on the product, we're just going to simply add the positive reactants. So simply take the 5765 and see what we get. In other words, we're already taking care of flipping the signs. I just want you to sum these two values. What do we get when we take these two values together? So we have a positive 5765 from the reactant side, and we have a negative 8292 from the product side, and it gives me a negative 2527 kilojoules. Alrighty, let me just make sure I'm saying that as clearly as possible. Over here, we keep it positive. Over here, we change it to negative, and we're just going to add the two together to get the heat of the reaction. We're already taking care of flipping the sign, so just sum the two components. Now there's another interesting part here. Do you remember this 2 that we had going on in front of the coefficient here, the number 2? Well, do you remember the overall question said per mole? Well, this is for every 2 moles. So we have one last piece of information we have to take care of. Is this value is what we calculated for 2 moles of our fuel. What would it be for every 1 mole? Well, I just want to divide that by 2, and now we get 1263.5. And now you can see that matching to your chemistry book from page 1, oops, I'm on the wrong page. Page 178, the energy change is negative 1256 kJs per mole. And so again, we just round a little bit different. And it said per gram. So remember our formula was C2H2? If we had 1 mole of C2H2, and I want to convert that into grams, I need the molar mass for C2H2. So carbon has an atomic weight of 12, but there's 2 of them in this formula. Plus, hydrogen has an atomic weight of 1, and there's 2 of them in this formula. The sum of 12 times 2 plus 1 times 2 is 26. The molar mass is 26 grams per mole. And so here, if this was the kJs for every 1 mole, we would take the negative 1263.5, and I know we had a little different decimal, but that's just by the rounding difference. They have it a little bit different, but we're doing it correctly. And I'm going to just divide that out by the 26 grams, which is equivalent to saying 1 mole. These are equivalent values. So I'll divide my 1263.5 divided by 2, and I get 631. Why did I 2? I meant to hit by 26. Calculator error. Let me back the bus up. 1263.5 divided by 26. That's what I meant to hit. And we get the 48.59. and I'll just round that, and that's a kJ per gram. Now let's review what we've done. Just to process with you. We were given a heat of reaction problem. Our fuel was acetylene, C2H2. Acetylene is a fuel, so when it combusts, we add oxygen. It comes out as carbon dioxide and water. We balanced it with a 2 to 5 to 4 to 2 ratio, and we were asked to calculate the heat of the reaction in kilojoule per mole. So even though when I balanced I had a 2 in front of the acetylene, no worries, we just calculated all of the energy content in each bond on the reactant side. We calculated all of the energy content on the product side, made it negative because bonds require energy to break, but they release energy when they form. And that comparison of the energy content to reactants to products for every 2 moles of our fuel, so we just simply cut it in half. For every 1 mole of the fuel, this was our heat content. We reviewed a little mole map work. When I changed my moles into grams, I used a term called molar mass, which is just me adding the formula weight off of the periodic table. The contribution of each atom to the overall weight of the molecule, 2 carbons at 12 apiece, added to 2 hydrogens at 1 apiece, gave me a molar mass of 26. So to convert my kJ per mole to kJ per gram, I used that molar mass and found the heat content in a kilojoule per gram. You'll see several of these on your sapling assignment as well. Nice thing is they're going to give us the structural formula, carbon tetrachloride. Notice there's carbon in the center and we have 4 single bond carbon CLs, plus 2 units of fluorine molecules. Notice they're drawing 2 units of fluorine, single bond fluorine. On the product side, it produced carbon tetrafluoride, CF4. So again, they've drawn that for us, C, single bond Fs, and 2 units of chlorine molecules. We'd like to know the heat of the reaction. And they're giving us a tool page right here. So let's kind of tabulate what's going on the reactant side and on the product side. On the reactant side, I have 4 CCl bonds. Do you see them? There's 1, 2, 3, and 4. Now it's a big mess, so let me just clear that up, but there's 4 units of that particular bond. So let's go to work and find a CCl. Here it is, 331. There's 4 of those. What else do we have? Well, we have 2 FF bonds. In each one of those, let's see, fluorine to fluorine. Here it is, fluorine, fluorine is 155. Don't forget to distribute. So what's the total heat content over on the products? On the reactant side? Make sure we leave it positive. So I'm going to hit 4 times 331 plus 2 times 155, and the total heat content on this side of the reaction is 1634, and that's in kilojoules per mole. Let's do the same sort of work over here. On the product side, I have 4 CF bonds in that first molecule. How much energy is that? A CF bond is 439. Remember that we're forming bonds just as a little memory tool that will end up making this negative, and these remained positive. How about over here? We have 2 Cl bonds, single bonds, but there's 2 of them. Chlorine to chlorine. Here it is, Cl to Cl, 243. And just to remind ourselves, we're making it negative. What's this sum? 4 times 439 plus 2 times 243 equals 2242. Since we already flipped the sign of the products, we simply are adding the two together. Let's take that negative 2242 and add to it the positive 1634. And we get an overall exothermic reaction with a difference of heat content of 608 kilojoules of energy. Remember, this means exo. Heat was released during this reaction.